We now turn to the hardware perspective. With our next speaker, we'll discuss key R&D advances in neutral atom computing and our ongoing industrialization journey towards scalable, high-performance quantum processors. Please welcome Pasqal's Chief Hardware Officer, Adrien Signoles.
Thank you very much. Thank you very much, Marco. Hello, everyone. Very glad to be here today with all of you to tell you about the efforts that we do at Pasqal to scale our technology that is made of those neutral atom quantum processors. So, at Pasqal, we are building quantum processing units, which are machines that are dedicated to process the information at the quantum level. And these quantum bits of information, we encode them, those so-called qubits, we encode them into neutral atoms. And so basically we have what we have on those boxes is everything that is needed to play, to capture, to manipulate those atoms. So we have laser beams that are going through a vacuum system where we have the atoms inside, and those lasers, they allow us to generate those optical tweezers that capture the atoms, and then we can shine other beams of light. For example, if you want to move the atoms from one side to the other, which allow us to go from the first image on the left, where you have some atoms in some tweezers, up to the image on the right, where you have all the atoms at the right position, for example. So at Pasqal, we are building a platform that is dedicated to compute at the physical level, where the information is encoded into physical qubits. And so what we do is we perform operations between the physical qubits. So I think that's the point. We perform operations between the physical qubits, or sequence of operations. We can measure the state of the qubits. And to do something useful, to have the possibility to implement applications, we are working at the R&D level to perform those operations with very high quality, to be able to address the qubits individually, and of course to scale the number of qubits. Okay, you know that the power of the processor at the end relates to the number of qubits that we have in the machine. So that's some R&D efforts that we do. What is very interesting is that with the same hardware platform, we can also compute at the logical level. In this case, in this paradigm, the information is encoded into a collection of atoms. And we now perform operations between those atoms, those ensemble of atoms, and we can, on top of it, do quantum error correction, which allow us to detect and correct for errors that may occur during the implementation of the circuit. It's the same platform, the same hardware. We just develop specific tools, for example, high-fidelity gates, all-to-all connectivity, the ability to read out and reload the atoms during the circuit, such that we can implement this type of digital and FTQC applications. What is also important to mention is that at Pasqal, we do those developments having in mind that we want to transfer them into a product at the end. We want to give access to our customers to those developments. And so there is a very important part of the work that is about industrialization, how we transfer those developments to something that is a product, and we take this very seriously, a product that is fully reliable and that we can use for large-scale implementation. So in this keynote, I would like to deep dive on 3 topics. The first one is about how we scale the number of qubits. The second one is how we move from the physical to logical paradigm. And the third one is about the industrialization part. All right, if you want to scale the number of qubits, what do you need to do if you want to increase the number of atoms you have in your array? First, you need to have more of those tweezers, to have more atoms captured. Second, you need to move them in an efficient manner, to be sure that at the end they are at the right position. And third, you need to make sure that while you are operating your system, you don't lose the atoms because of some imperfection. In the work that we have done recently, we have been putting together 3 different pieces of innovation and technologies. The first one is to develop a new optical architecture that is based on high-power lasers and high numerical aperture optics that allow us to generate many of these tweezers. The second one is we have been really optimizing and working a lot on the way we perform the moves to increase their efficiency, and we've been working on implementing a two-step moves that I will illustrate in the next step. And the third, which is also very important, we've been working on a new design that is based on cryogenic pumps that allow us to cool down the environment around the atoms to reduce a lot the residual pressure that we have in our vacuum system and to avoid any collisions between molecules that could fly around and the atoms that we have in the tweezers to make sure that nothing bad happens while we are making those arrays of tweezers. And the results combining all those pieces of technologies is that we have been obtaining those very beautiful images. On the first one, you see all the initial loading of our register. We have more than 2,000 tweezers there. And then you see after the first step that it's almost perfect, but still, if you look carefully, there are a few defects. And then after the second step of rearrangement, we have a perfect array without any defects with 1,024 atoms. If you want to learn more, actually, you have a blog post that has been published and a scientific paper also on arXiv. Okay, so that's about scaling. Now, what about logical qubits? Again, so physical qubit is a single atom. A logical qubit is a patch of atoms where you encode the information with some kind of redundancy such that if there are errors occurring, you can detect them. So what is needed to compute with logical qubits? First, you need to have robust physical qubits with long lifetime, high coherence time. Second, you need to be able to operate, to implement reliable operations between those qubits. Single qubit gates, two qubit gates, for example. Third, you need to be able to connect any of the qubits in your system together to entangle them. This is what we call the all-to-all connectivity. Fourth, you need, of course, to be able to read out rapidly the state of your qubits. And last, you need to define the way you will encode the information into these logical qubits and the way you will decode it later, which is basically defining the code, the error detecting or error correcting codes that you will use. So what we have done is we have worked on this to implement the first example on a real system on one of our machines using a code that we call the 422 code, which basically is using 4 physical qubits to encode 2 logical qubits. In this circuit, we are just trying to prepare the 2 logical qubits in a specific state, which is the most simple state, which is the 0-0 logical state, which actually means that your 4 physical qubits, they are in a quantum superposition of all in 0 and all in 1, as it is written on the left. And so this circuit is basically a sequence of operations that we implement on our atoms to be able to prepare that. And here are the experimental results. So ideally, we expect, if there are no errors in the circuit, we expect to have either all the qubits in 0 or all the qubits in 1, which are these 2 big bars. Of course, there are errors, and we know that because atomic operations are not perfect. So we see errors, and we end up with a probability of 40% to be in the right state. But now if we use our capability of detecting the errors that occurs because of the code that we have been using, we can remove most of the errors, and we end up with a probability of 90% to have prepared the right state, the 0-0 logical state. This is really to illustrate in a simple example how error detection can improve a lot the performances of your system. So I told you about how we scale the number of qubits, how we can play with logical qubits. Again, the true challenge actually is to do that in such a way that later you can really build on those developments. You can use them in other platforms, combine them with other type of developments, and later transfer them into the product. So now I would like to tell you about industrialization, which is really a major differentiator that makes scaling possible. Industrialization is something that goes from the way you design up to the production to be able to unlock this rapid transfer from what is done in R&D labs into products. It's, of course, about putting in place the right manufacturing capabilities, putting in place maintenance activities, but it's also about the methods you use to design. It's about the test that you will define to verify each step of the development. It's about the documentation, the process that you put in place. It's all that. And it's very important for a company like Pasqal. We have decided from the beginning of the company to invest on industrialization. And it looks maybe obvious, but it's not something so easy to do. Because for a deep tech company as Pasqal, you need to do it in a very agile way. We want to be able to do at the same time very deep research and to manufacture reliable products. So we need to have the right process to do that. It's something that has a cost, of course. It requires capabilities, equipments, resources to do it. And it's something that you have to do gradually to adapt at each time, at each step of the company to make it efficient. But at the end, it's a very strategic asset for the company. It has really two values that are very important for us. The first one is that industrialization is the sustainable way to commercialize multiple QPUs around the world. It's the way you can have reliability in the manufacturing. It's the way you can deliver systems worldwide. It's the way you can upgrade, you can have services at a cost that is under control. And it's also an accelerator for R&D. It's also something that you can really use, you can leverage on industrialization to go faster on your developments, to focus on the new breaks that you want to develop, to integrate rapidly, and at the end to reduce the time between R&D and product. So it's a strategic asset, and we already see the benefit of that. It has been said, of course, before, we have been able to deploy multiple systems around the world, and this is a very, very significant achievement. And we will continue, of course, doing that. We have QPUs, products that have been delivered. We have also internal machines that we are using. I showed you how we are using those systems internally to scale the number of qubits, to perform logical computation. We will continue doing these developments, having in mind that we want to transfer them rapidly, and this will really fuel our future product. All right, so with that, I would like to thank you for your attention.